Hi everyone, welcome to a new video on informatics. Last day we had talked about thinking recursively. In today's video, we are going to try to extrapolate our ideas to see how we can apply those concepts to know more about dynamic programming. We are going to also implement our problem of misaddressed letters, try to write the solution and the code in dynamic programming and understand how it's better than the normal recursive approach that we have. Join us in, it'll be a lot of fun. So we have dn equal to n minus 1 times dn minus 1 plus dn minus 2. If this recurrence relation doesn't look familiar to you, I'd suggest you take a look at the link in the description below for our previous discussion on thinking recursive. So as we have seen, this is the recurrence relation for the derangement problem. Let's write it down that we are talking about the derangement problem for sure. It was the problem of n letters and n envelopes where we want none of those n envelopes to have their corresponding correct letters. Now, the recurrence relation we had arrived at. And let's talk just a little bit about the base cases. So the base cases would definitely be, ask yourselves, what should be the preliminary base case for this problem? Of course, n equal to 1 should be a good idea. What would n equal to 1 imply? N equal to 1 would definitely stand for one letter. Now, if there was only one letter and one envelope, then in how many ways could you possibly arrange the letter into envelopes such that none of the letters goes into its correct envelope? Obviously, goes without saying there would be no such arrangement at all, right? If there's only one letter and one envelope, there wouldn't be any possible way to have a derangement. Which just goes on to say that D1 would most definitely be 0, correct? Now, the next value that we'd be interested in is definitely D2. N equal to 2 would correspond to a case of 2 letters and 2 envelopes. A very rough diagram for us to refer. 2 letters and 2 envelopes. The only correct derangement for this would be letter 1 going into envelope 2. And letter 2 going into envelope 1. So definitely goes without saying we will have D2 as 1. These two would be our base cases. Whenever we have a recurrence relation, base cases are of utmost importance because if we do not have the base cases, we wouldn't be able to build the higher ones. And essentially that's the concept of recursion. Building on the higher cases using previous ones, as we know, because a function calls itself, as we have talked about previously as well. So the point is that we can generate the value of D3 using the values of D1 and D2. We can generate the values of D4 using D3 and D2. We can generate the values of D5 using D3 and D4 and so on and so forth. In general, as you can see that we can generate Dn using Dn minus 1 and Dn minus 2. So just as a short trial, if we want to find out what the value of D3 is going to be, it shouldn't be a very difficult ask for us. N minus 1, obviously since the argument that we are passing to this function is n, and n minus 1 would definitely be 2 in this case because it's 3 minus 1. So 2 times D1 plus D2, where we have already seen that D1 is 0 plus D2 is 1. So 2 times 1 would be 2 itself, right? And then we would have D4. If we want to find out D4, that's exactly, we're going to do something very similar. D3 is 2 and D2 is the other thing that we'd need. So practically what we're going to do is 4 minus 1, which would be 3 times D3 plus D2. Where obviously D3 is 2 as we have seen and D2 is 1. So 3 times 3 equals 9. So in the previous video where we were talking about 4 letters and 4 envelopes, the problem that we had introduced ourselves into recursion with, the answer to that problem was actually 9. This is something that we just got to know, right? And so we had talked about it. Like if these are the smaller cases, we might have satisfied ourselves with such an output or such a result. However, if we're looking for higher values, well, what if we want to know in how many ways we can totally derange 40 letters? In how many ways can we derange 50 letters? So on and so forth. Something as high probably as even 1,025, because we know in competitive programming, it's all about the larger test cases. That is where your algorithm is truly tested and you really want to meet obviously the time requirements of the output file. So dn equal to n minus 1 times dn minus 1 plus dn minus 2 is the recurrence relation that helps us get to this answer. But how exactly would a computer process this recurrence relation? If you have implemented recursive functions before in Python or in any programming language for that matter, you know exactly how it brings the recursion tree into play. At this juncture, if I briefly go into the discussion of Fibonacci sequence, I think it will be helpful. We have all heard about the Fibonacci recurrence relation. We know it's fn equal to fn minus 1 plus fn minus. Now, how exactly would that plan out? So if we have f6, for example, f6 would work. And obviously, let's also mention the base cases. The base case for Fibonacci reconciliation would be f1 equal to 1, f2 equal to 1. So now f6 would definitely be calculated using f5 and f4. F5 would require f4 and f3. F4, again, here you would have f3 and f2. F3, here again you have f2 and f1. F3 for f2 and f1 again. So you can see that we'll keep on decomposing. We'll keep on decomposing using the reconciliation itself. We'll keep on decomposing the value of f6 until and unless we have the base cases at our leaf nodes. So you can see that all these leaf nodes currently have the base cases. Like, f2, you know the value for this. F1, you know the value for this, and so on and so forth. You can see that all the nodes that you have in your respective last layers of this tree are the leaf node values. So then you can put in these values, and that is how exactly the value for f6 is propagated at the top. So let's say, if we put these values of f1 and f2 here, then you would add up these values to get a 2 for f3. Again, you know that let's do this thing. Let's populate the values of all the base cases in our leaf nodes. So f1 and f2, let's assign a 1 for them individually. Wherever we see those, f1 is 1, f2 is 1 as per the Fibonacci problem. Now, obviously, how do we calculate the value of f3? How does the computer calculate the value of f3? Essentially, f2 and f1 gets added up, 1 and 1, that gives you 2. f3 and f2 then would add up and give you 3 for this f4, right? And then f4 and f5 you have here. For that, again, you'll have to come to the left flank. So you have f1 and f2, you have 2 here. f3, again, you have 2 here. You calculate and you find 2 here. So then you find 3 here. And then for f5, you find that this f4 and f3 would contribute to the value of this f5. You'll have 5 here. And finally, f5 and f4 would add up on the respective left and right flanks of the tree to give you 5 plus 3, 8, which would give you that f6 is basically 8 is what we're looking for. And that's exactly how any recurrence tree would basically operate. What's the problem with this? The only problem that would apparently meet the eye is the fact that you have multiple instances, obviously, of f3. And every single time a call is made to f3, for example, not only f3, any of these intermediate values in our recursion, any of these intermediate values that we sort of process, are basically overcomputed because you're making a recursive call to the function again and again to calculate the same value f3. Imagine you do it for the first time here. Then again, when you encounter f3 on the right flank of your tree, you again resort to f2 and f1 just to find out the value of f3, right? And that is basically an overkill in terms of the time complexity that we are having. If you're calculating the same thing over and over again, making recursive calls to the function, that is basically, in plain and simple language, it would be a waste of time. And that is what dynamic programming as a programming paradigm seeks to improve. So the time complexity for this, for a simple recursive approach, if you just relate to the way the tree spans out, you can see that f6 gives you 2 alternatives. If you think about these branches of the tree as alternatives, as it is going to be so many times in the problem statements, they're going to give you 2 alternatives. That is this one profitable or is that one profitable? Or you might have more than 2 alternatives even. You can have something like 3 alternatives. In that case, the question is always which is the best alternative to take. However, in order to decide which is the best alternative to take, you would have to explore all the paths first to realize that, yes, this is the way, this is the route that we want to take. So if you think about F5, F4 to be 2 alternatives as in a schema, then you would understand that for every point of time, you have 2 alternatives, as in F6 gives you F5 and F4, F5 gives you F4 and F3. We all know that those are basically the requisite values to calculate the value of the higher case. But if you think about choices, then that could be another way of thinking about it. And at every point of time, if you have 2 branches emanating from any particular node, you basically have 2 choices every single time. So your complexity would be something of the order of 2 to the power n. I mean, you would have n in your index, right? Which means that you would have something close to an exponential time complexity. And as we have talked about this before, exponential time complexity might be okay for cases below 20, below 30, below 50 even, if you're patient enough. But then once you go on to the higher test cases, it's definitely not going to be able to keep up pace and not going to be able to meet the time requirements of the online judge, or in, even if you're trying to simply write the code, as we shall try in a few minutes. If you simply try to execute the code and try to measure the amount of time being taken, you will see that you will have to wait for a longer time as and when the values of n rise. So definitely it's going to be more beneficial if we think about something that can help us cut off this exponential nature of the algorithm and try to make it a little better. What could that strategy be? That is exactly where dynamic programming makes its entry. So DP, or dynamic programming, is basically composed of two caveats if you think about in terms of programming. It's recursion plus memoization. So the recursion component is definitely something that we have talked at length about. We have already understood what recursion is, why we use it, how we use it. And in a minute ago, obviously, we talked about how the recursion tree calculates the values, how when you actually write the function, the flow of code propagates and gets you the output value, essentially. But this is a term that's comparatively new to us, and we would want to know whether this is the secret to optimization. It turns out that it is. Memoization is basically use of a suitable data structure to store the intermediate values. It's effective storing. It's effective memoizing of the values. Because if we manage to store some of these intermediate values, that would entirely cut off that entire point of overcomputation, calculating the same things over and over again. For example, even in a small incantation of F6, we ended up calculating F3 3 times. Imagine if you were calculating a slightly larger value. For example, even if you think about 2 digits, right? Even if you were calculating F90, just try to visualize the recursion tree for F90, even in case of Fibonacci. How many times would you end up calculating values such as F50, F60, all of these intermediate values? You would calculate them over and over again, make recursive calls to find out the value. And that's where, as we have talked about earlier, that's where we're losing out on time. Instead, what if we had a data structure? Something as simple as an array, probably, guys. Obviously, you should be able to, with all your programming experience, you should be able to link to the fact that, okay, it should be as simple as using an array to just store each of these values. Instead of calculating them, instead of going through the recursion tree, parsing it, calculating it over and over again, if we simply store it as an index, store it as an element of an array, indexed by its individual positions, then that would just mean the world to us, right? We would definitely have that value stored. And the next time we need it, instead of going through the same recursion tree and calling its lower values, we can simply access it from the array. And we all know that accessing something from an array, accessing something from any data structure like an array is constant time operation, right? It's a constant time operation. It's big O of 1. You just need to access the value that you have stored in an array. So imagine if you have the value of F3 stored in an array. Now just walk with me along this recursion tree as we just do it once more, this time with an effect, with an enhanced spotlight on what we are trying to do using memoization. So if you have F6 and that decomposes to F5 and F4, and then that asks you to decompose into F3 and F2, and let's say this is the first time whenever you encounter a new intermediate value, you push it into an array. Whenever you encounter a new intermediate value in your recursion, you calculate it and immediately you push it into your memoizing array. The next time you require it, let's say hypothetically we require it in the left flank, the next time you require it, you simply fetch it from the array rather than going through again the decomposed cases F2 and F1 and propagating it and trying to find the value again, right? You simply fetch it from this array. If we're calling this array L, then the value of F3 would be stored here. And let's say the value of F3 is 2. So the next time I need F3, I'm not going to calculate it recursively. Rather, I'm just simply going to fetch it from my array. So once you see a new term, you calculate it. Definitely, that's the first term. You definitely need to calculate its value. And then you immediately store it into the array. Ever since you required it, you'll access it from the array, making it a constant time operation therein, right? So this would dramatically reduce the time complexity required. And that is what gives dynamic programming its edge. So basically, talking a little bit about theory, a dynamic programming problem nearly always has an optimal substructure and overlapping subproblems. So an optimal substructure is due to the recursive nature of the problem. In order for you to apply a dynamic programming solution, to conceive a dynamic programming solution, you need to have a recursive approach and you need to come up with the recurrence relation. Once you come up with the recurrence relation, you have to have a suitable data structure that you can use to memoize the values of the recurrence relation that you have. Once you come up with the recurrence relation, you need to have a suitable data structure to store those intermediate values, to store every single value so that you can use it to build on the higher cases. And that is what is going to help you come up with the optimized solution. Let's see this in action in code. Join us on the other side. So let's have a look at the code that we have. And we're going to talk about both of the approaches, the simple recursive approach that we were talking about, and the dynamic programming approach, obviously, as well. So this is for the derangement problem. We did use the Fibonacci recurrence relation to get ourselves acquainted with the recursion tree and all of those concepts. And you can see that concept is easily something that we can extrapolate to the idea of derangements, because essentially the recurrence is similar. And also, That's exactly the way you would expect any recursion to behave, more or less. So at least in our case, it will hold true. For the first approach, which is using plain and simple recursion, the code is absolutely simple. You can see that we are starting off with a import of the time module. This is essentially because I want us to have a flavor of the amount of time it takes for the code to execute for some of these cases. So that it would effectively it would help us compare the two approaches. Compare the two approaches as in the recurrence relation-based approach. Only the pure recursive approach and the DP approach. So basically, let's call it the non-DP and the DP approach. So first, we are only just going with the simple recursion or the non-DP approach. So as you can see, we have a simple derangements function which takes n as the input parameter. It checks if n equal to 1, return 0. If n equals 2, return 1. Take a moment, guys, to identify what these two are. These two are our old friends, right? Base cases. They act as stopping criteria for the code as well. Because, think about it. When you pass in a value exactly like, let's say, 6 or something, obviously control is transferred to this else statement. Why would control be transferred to the else statement? Because simply, if it would satisfy none of these two blocks, right? Neither n equal to 1 nor n equal to 2, which would definitely justify why control is being transferred to the else statement. And then, so you would require, so the algorithm would keep on processing the value exactly as we saw in the recursion tree, like F6 branching out to F5 and F4, F5 again individually branching to F3 and F2, F3 and F4, and F4 again branching out to F3 and F2, and until and unless you reach the base cases. So that is why, since if you just recall the fact that we had said that base cases would be the leaf nodes, that's exactly the philosophy that's being upheld here, because you can easily see that these are the cases where your code would stop processing and would actually return you the definite values to calculate. And then obviously using propagation, you would get the answer for your required case. So you have if n equal to 1 returns 0, if n equal to 2 returns 1, and then in your else block you have return n minus 1 times derangements n minus 1 plus derangements n minus 2. By now it should be something that we are really familiar with. This is indeed our entire recurrence relation. And that's it. This is the simple recurrence relation block, right? It's a simple user-defined function. See, the good thing about functions is that we can, in programming is any function, it can be non-recursive or recursive as well. It just depends on what you have inside it. So you can easily see that this function is recursive simply because derangements of n, in order for it to compute its value, you are having to make a call to derangements itself. So whenever a function calls itself, recall, this is something that we had mentioned earlier. Whenever a function calls itself, its nature is recursive. So there you go. Derangements function is all done, and we are good to simply test it out, right? So we have started off, let's start off with a slightly lower value like n equal to 5, for example, or probably let's try out n equal to 4. If you recall, we had an answer for n equal to 4 as 9. Let's really check out whether that's the output that we are getting. And okay, so you can see the number of derangements here is 9. However, you can see that we have begin equal to time.time and end equal to time.time in the main part of our code. This is something that I'm doing just to show you guys the amount of time it takes to execute the code on our local system. This would vary according to your systems and all, but it would be interesting to try this out as an experiment. So n equal to 4 gives you 0.0099 seconds, which is no surprise actually. Let's try out a larger value, for example. Let's try out n equal to 10 and let's see what sort of time that takes for a pure recursive approach. So you can see that it takes 0.0. So, as we have studied, and if you know a little bit of algorithmic complexity, if you have studied a little bit of design and analysis of algorithms, you know that lower cases are never really reflective of what the actual scenario is when the cases grow higher. Whenever you're trying to analyze a time complexity for any algorithm, you should never do it for the lower numbers. You should always try and do it for the higher numbers, because that is when you really get to test an algorithm. That is when the mathematical trends are visible, is something that we know. Let's try out n equal to 25 with our simple recursive approach. And you can see that the time has escalated just a little bit. You have got 0.03.05. We have got 0.03053 as the amount of time that it took. And you can also see that the number of derangements value also is quite large. You can, let's just try out, maybe just go one level up and try out 35. And you can see that we might have to wait a little, really. And yeah, you can see that now it's beyond 0, right? You have reached 2.6769661 as the amount of time taken. Slowly move up higher, and you'll see that the time taken actually escalates a lot, right? Let's go on to 40 and see. Let's test our patience out in a way, right? If you're having to wait for a while, that is indicative enough. On a system, on your own local computer, if you're having to wait for a while just to get the output for a case of n equal to 40, that is pretty indicative of how not optimal your algorithm is. And I mean, that is exactly what dynamic programming seeks to address. That's a problem that dynamic programming tries to fix. And this is obviously simply because the number of recursive calls that you're making for those intermediate values grows manifold, right, guys? And I mean, you can easily see that it took you 29.77 seconds for n equal to 40. I think that's a good point for us to just move over and try out the DP approach that we have in the next cell in this same notebook. Let's just try that one out now. Before we try to execute the dynamic programming code though, let's see and let's compare the difference that we have in the derangements function definition out here. What exactly has changed? If you see, you have an array declared, guys. And this is that very memoization array that we were talking about. This is that very array that we are using to store every single value. It comes up as a new item in our recurrence relation parsing, right? So you have derangement equal to 0 for I in range n plus 1. What essentially is being done here is that you're filling up an array of length n plus 1, and you're filling it up with zeros, all zeros initially. The reason why we do this is because we want to be able to edit. We know that lists in Python definitely are mutable structures. So when we have the main loop that actually affects the recursion in place, we can go and change derangement of I. We can just simply index this DER array that we have, and we can just say that DER of I equals something. We can set that value, and definitely we're going to set that value in agreement with the philosophy of the recursion that we have. So, I mean, it just is as simple as it gets. DER of 1 equal to 0, DER of 2 equal to 1. Earlier in the recurrence relation, we had two conditionals. We had two conditional statements to check out that if n equal to 1, you return 0. If n equal to 2, you return 1. These were our base cases. That's how we were representing the base cases. But here, since we're going to use the array to store those values, and also within that array itself, the higher values are going to be computed, you can see that DER of 1 equal to 0 and DER of 2 equal to 0 and DER of 2 equal to 1, is exactly how we set up the base cases. This is exactly how we set up the base cases. And now we move on to the main loop, right? So for I in range 3 to n plus 1, so definitely you want to start from 3. And I mean, that just goes without saying. If you remember what we were doing on the Jamboard, we had started off with D3, right? We wanted to calculate D3. I mean, goes without saying, right? Because D1 and D2 were our base cases. So the first value that we essentially computed using the recurrence relation was D3. And here in itself as well, we want our looping variable I to start from 3 and go up till n and just fill in these values, right? So DER of I equal to I minus 1 times DER of I minus 1 plus DER of I minus 2. Should come as no surprise at all, because this is exactly the derangement recurrence relation rephrased, isn't it? Earlier we had concrete values in n itself, like n minus 1 times derangements of n minus 1 plus derangements of n minus 2. The only difference that we have here, guys, is that here we have it inside a loop, and not only do we have it inside a loop, we also are assigning these values that we are computing. What is the value that we are computing? Ask yourself quickly. You have I minus 1 times DER of I minus 1 plus DER of I minus 2. This value that you just saw is getting assigned to the value on the LHS of your equation, quite naturally, right? So DER of I gets populated every single time in your loop as I minus 1 times DER of I minus 1 plus DER of I minus 2. Just visualize one thing though. When your loop goes through its first pass, it's for I equal to 3. So it tries to find out DER of 3. It tries to populate DER of 3. When it tries to populate DER of 3, obviously I is 3, so I minus 1 turns out to be 2. And what else does it expect, guys? It just expects DER of 2 and DER of 1. Do we have DER of 2 and DER of 1 with us? Well, of course, yes, because those are the base cases that we have already initialized. The next pass you would be looking for, ask yourself, it would be definitely I being incremented by 1, so it would be I equal to 4. We would be trying to populate DER of 4. What are the requisites to populate D equal to 4? I mean, what are the requisites to populate DER of 4? You would require DER of 3 and DER of 2. But wait a second, DER of 3 is something that we just calculated in the previous pass. Not only did we calculate it, we stored it in the index 3 for our array. And just because we have it stored, this time when we require it, with this DER of I minus 1, which obviously invokes DER of 3, it is just a plain and simple access statement from our array DER. It's a plain and simple access statement from our array DER, which is obviously a constant time operation, which makes a world of difference. It just makes the most stark difference that we can obviously imagine, because that is where the code differs, guys. That is where the code differs. Earlier, when we were making this, we were making a call to the derangements function itself. This time, I'm not making a call to the derangements function itself. My philosophy is still recursive, but what I'm trying to do is I'm just trying to pick the value up that I just computed using my recursive value, using my recursive philosophy. I'm just trying to pick the value that I last computed because I have it stored in a suitable data structure. For us here, it's an array. The array is called DER. So I pick it up and I get my values calculated. Finally, I'm just returning the last value of my array, which is DER of n, because that is where my n plus 1th value would be stored. And that's exactly what I'm looking for. Let's just go ahead and check what we have. If you're intimidated just by the sight of this n equal to 1000, well, let me tell you, there's no reason to be scared because dynamic programming can deal with it. Let's just try out even though for n equal to 10 something probably, right? And let's just see. So yeah, answers were matching. Let's do one thing. Let's try out for n equal to 4 and let's quickly see if we have 9 again. Yeah, definitely it's 9. So correctness is something that we are okay with. Let's move over quickly to n equal to 10. And we would see that number of derangements that we're getting is 1334961. Time is still close to 0 seconds. We are not really bothered. Let's try n equal to 25. If you remember, n equal to 25 was somewhere around 0.3 seconds or something for our non-DP approach, but you can see for us here, it's definitely still 0.0. Now, we definitely remember the challenges that our non-DP approach, our plain and simple only recursion approach had with n equal to 40 and n equal to 35, right? So let's give our DP approach the challenge of finding out the value for n equal to 40, and let's see the amount of time it takes. And there you go. There's the moment of truth. Guys, you can compare both of these values. You can see that the values obviously match. Correctness is something we have dealt with. But look at the time for execution. The time taken for execution for our non-DP approach is somewhere close to 29 seconds. Whereas when we implement memoization along with the recursive philosophy, as in where we implement the dynamic programming approach, the time taken is still 0 seconds, guys. I mean, obviously it's something, but it's as negligible as it gets. So we can still account for it as, close to 0 seconds, right? So you can literally just think of 40 and just let's try to look for a few higher values maybe now that we are, obviously that must have boosted up our confidence. So let's take a jump to 100. Let's see how fast our DP algorithm can generate the answer. And there you go. It's not a challenge. It doesn't obviously matter whether how large a value you put. At least, even if you stick to 3 digits and all, it is really not going to make a difference. As you can see, time taken for execution is still in the order of 0.003, which is a huge deal. Imagine having to do 100 with this. You would definitely have to wait for a few minutes. That's no secret. Let's try out n equal to 600 maybe, or let's go on to 4 digits probably, n equal to 1000, and there you go. The output is there in a flash. It is still in the order of 0.003 seconds. Now, this is, if you've done a little bit of, as I said, if you're acquainted a little bit with design and analysis of algorithms, you would be aware. And we did talk about the fact that why the first code is definitely something that has an exponential time complexity. Then just try to think about this. What would be the time complexity of this? Here, all that you're doing is essentially looping across an array of length n. Guys, think about it. We are essentially just looping across an array of length n with the nature of values that we are populating, with the kind of operation that we are doing inside of that scan that scans through n values is recursive. The philosophy is recursive, but then we are not making those unnecessary recursive calls because we are using an array to pick up the intermediate values. So all that we are requiring is a pass through. All that we are requiring is a pass through our array of length n, which just goes on to say that the time complexity that we are looking for is definitely big O of n, right? So big O of n versus something that's exponential, we all know who wins the race, right? And if you're really interested, try out a small activity at your home. Try out this code, try out these 2 blocks of code on your own, and then just try to capture the amount of time taken, right, for various cases. And then plot a curve, guys. Plot a curve with n, the size of your input on the x-axis, and the time taken on your y-axis. Do it for the non-DP approach. do it for the DP approach and just see the stark difference. If you just plot it for values, go up till values as large as 10 to the power 5, 10 to the power 6, maybe that's where the fun begins for our DP approach at least. But then if you're patient enough and if you just capture all those values, and then you can use something as simple as matplotlib to just plot those values and get the curve, you will see how the nature of the curve that's produced by the non-DP section of the code is actually exponential, as opposed to this one, which is going to be something close to a straight line, right? Because, it would be linear in behavior. It's not quadratic at all. You can see that, there definitely it is going to be a single scalar pass. A single linear pass. Sorry, it's definitely going to be a linear pass, okay? And you can see that, obviously the rate of increment of something that rises linearly is definitely going to be way slower than something that rises exponentially. And the more slowly our values rise for that curve, the more slowly time taken for execution rises with respect to our input size values, the more faster our algorithm is. And that is how transformative dynamic programming is as a problem-solving strategy. I hope you enjoyed the video, and I hope this concept is something that you will be able to use to solve problems in the future. Thank you.